Hi friends, this is Rishika. This would be my 7th video tutorial on data stage and my first video tutorial on parallel jobs. So yeah, as I said in my previous video, this video is a initial start for the parallel jobs before we go on to the designer and design some of the parallel jobs and learn more about the stages. So here we go. Let's see the introduction part. So I have been repeating it several times that the parallel jobs run on multiple nodes, so just remember that. And what happens is when you design a parallel job, basically InfoSphere data stage generates it. In the background, it generates its own script, like the background language. It's called orchestrate shell language. It's or else OSH script. So basically, all the stages, all the things, everything like to be data stage need to understand in its own language, right? So that's how that is what its own language is, orchestration language, sorry. So yeah, except the transformer stage, which uses C++ code. So yeah, so that's orchestrate. So if someone asks, this is one of the interview questions. So if someone asks what's a background for the data stage, do you have any, do you have any knowledge about the how what exactly happens in the background when you design a job? Yeah, you can just undoubtedly say them that yeah, every stage and everything gets into like converts into an orchestrate language, so that the data stage, this conversion happens internally. So the data stage once understands it and then gives output or and transformations and all that functions. Okay. So basically, orchestrate is like orchestrate language is more like Unix shell, is like syntax is more like Unix shell. You need not know more about in this video, because it's pretty basic for beginners for better understanding. So yeah, it has like operator name schema, and every operator has input sets and numbers sequentially starting from 0 and virtual data sets and all other functions. I don't want you to confuse. Yeah, so that's it. In the background, the data stage creates its own language called orchestration language. Okay, so yeah, what makes parallel jobs more important is that in real time we design most of them. 95% we go for parallel jobs, apart from the sequences, which is like automation of the jobs. So yeah, parallel jobs have more stages. If you have seen, the server has only a few stages in the processing and all that, but parallel has like more stages and have lot more settings than the server jobs. For each stage they have like multiple functions and multiple settings that we need to have, and multiple options we do have according to our requirement. So yep, that's the other thing. And the other thing is processing environments. When you come to the parallel thing, we do have two different processing environments basically. Processing environments are basically the environment in which you run your parallel jobs, right? It is defined by like system architecture and hardware resources available and all that functions. So basically we have two different processing environments for parallel jobs. One is SMP, which is symmetric multiprocessing, and MPP, which is massive parallel processing. So if someone asks, this is also one of the important data stage questions. So basically the guys start with so tell me about your latest project or recent project architecture. So that's when you need to know symmetric multiprocessing or massive parallel processing. Mostly it would be MPP, because yeah, I'll tell it. So yep, so coming to the symmetric multiprocessing is like they have like shared resources. Like they have like a few process, let's say three process, and these three process have the same hard drive or same resource which are shared among these process. So that's how it works. Basically they have like a single operating system. So they have like single operating system, and then the process, these three process, for example, these how many process, let's say three, right? Okay, so these three process communicate through that shared memory. So yeah, that is how it works. So yeah, so basically, I mean, they have like shared memory, shared storage, and single operating system. So basically, the workload for this, when you design a parallel job on SMP architecture, the workload is distributed across the processes in the system. So yeah, I mean, it's not really as fast as, because it's the same. I mean, the processors are using the shared resources, but still, if you can increase the number of processors, add memory, add increase storage, yeah, the scalability of performance gradually increases. So that's how it works. And the other is cluster or MPP, MPP, which is massive parallel processing. It's also known as shared nothing. By the term, you can say shared nothing, right? Yeah, shared nothing means it doesn't need to share any resources, either hardware or not software. It hardware resources or like storage, memory, and all that stuff. Yeah, so it doesn't need to share anything. It has its own operating system. Basically, it's like they have like their own operating system, and they have their own memory. They have their own memory and resources. So because they have their own memory and their own resources, obviously that's much faster, right? So yeah, most of the projects, like, I mean, depends on the complexity of project and cost of the project and all that. Smaller projects go for SMP, and but like SAP projects and all that, like higher level projects, they choose MPP because they need to be fast enough and the performance need to be good enough. So yep, that's about SMP and MPP, which are like processing environments. And next is processings. We know processing environments, right? So now we need to know how are parallel jobs processed. So basically, there are two types of processings: pipeline parallelism processings. I mean, parallel jobs, right? So parallelism. There are two types of parallelisms: pipeline parallelism, partition parallelism. And the other thing is, mostly this is a common type. Basically, we are combining pipeline and partition, so making it much more efficient. So let's learn what's pipeline and what's partition parallelism. So pipeline parallelism, it's like process the data simultaneously. So how do you know that is, you have source and like place any stage or something, and then target, right? You see the diagram here: source, any stage, and the target. So what happens in this is, once you start running the job, the stage, let's say you have like three processes. Okay, three processes in the sense, I mean, the config file, the nodes which we are using as per your config file is three. Let's say it's three. Okay, so what happens in this pipeline parallelism is, let so basically okay yeah, so basically I'll explain with an example so it will be much more clear. So we do have like two columns: merchant ID and merchant name. So merchant ID, two columns with how many records? One, two, three, four records. Okay, so we do have two columns with four records, right? So what happens is, when you have like two columns, two different columns or two different fields with four records or four rows, so what happens is, once the first row, it depends on the way we choose the partitioning technique, which I'll be dealing with in like next slide. So yeah, so once, let's say the first record is read, okay, A100, and then okay, let's say A100 is read and the corresponding Walmart is read. Okay, so it's, as soon as it is read, then it is moved on to the next stage. It doesn't wait for all the other three rows to read and then completely pass it on to the next stage. It doesn't wait that way. So as soon as the record is read, it is moved, and as soon as here it's read, it's written to the target. So that's how it works. So by the time, let's say, by the time the third record is written to the target, it may be happening that still the second record is being read by the source stage. So that's how it works, like pipeline one. It doesn't, okay, let's say we have I mean, the term says pipeline, right? So let's say we have like some pipe, and let's say we have put some ball into that. As soon as we put the ball, it passes through, right? It doesn't want next push or something, or the next ball to come and push that. it passes as I mean till the dead end, right? So yeah, exactly the same thing. It doesn't wait for the second record, or it doesn't wait for the everything. I mean, it doesn't move as a group. As soon as it's read, and then move to the next stage, and all the transformations are done, and then this. But the thing is, it needs to be like because we were running it simultaneously, because it's running simultaneously, right? So obviously the disk usage is less, and because it's not waiting for all the records, to be written. I mean, one like all the records to be read at source, and then move to the data. I mean, any stage, and then to the target. That is reducing obviously the idle time on the process. So yep, that's how it works. So yep, I think I made it clear. Okay, so let me just summarize it. I'm sorry. So yeah, when we take this example, let's say the first record is read, and then the first record doesn't wait for all the other records to be read. As soon as the first record, or any other record, like any other record, is read, it's moved to the next stage. And as soon as this is read, it doesn't wait for all the other records, and then it moves to the target stage. It is written to the target stage. So let's say by the time the fourth record is being written to the target, it may be happening that the second record or third record is still being read by the source stage. So that's how it works, like pipeline. And next, coming to the partition parallelism. Partition parallelism is, it's like what do I say? It's more like basically the incoming stream of data, like the huge volumes. Basically, this partitioning parallelism is for huge volumes of data. So when there is like huge volume of data, it is divided into subsets. So I mean, yeah, so basically it's divided into subsets. So basically the best advantage by partitioning the data, like, is dividing it into subsets. When you have like 10,000 records, and you I mean, when you have like 1,000 records, and you make it like 250 let's make four subsets, so 250 each. It's easy for the data stage to make like 250 records read at a time, right? So we have four different sets, so we are making simpler for the data stage to read, so that increases performance. So because I said it is divided into subset, these subsets are actually called partitions. So that is how it got named partition parallelism. So these partitions, the number of, this division of the subsets depends on the number of nodes your project is using. Let's say if you have like 4 nodes, so it's the subsets divided. It doesn't depend. If your project has like 8 nodes, it doesn't mean that your records, your incoming volume of data is split into 8. It depends on the config file which we are using in that particular job. Let's say I do have eight nodes in my project, but I'm using only 4 nodes in my project. In my job. Sorry. So now when I put this partition parallelism, it means that my huge volume of data is being partitioned into, is being divided into 4 partitions. So that's how it works. So as once that data is partitioned, and then every stage is like, it's like every stage is split into 4 partitions. So everything like node by node, node by node, node by node. And then once the partition and once the transformations and everything is done, then it's all collected back, all the partitions are collected back and written to the single data source, or else, depends on your design and code and all that. And the the biggest advantage, or the important thing about the partitions is, these partitions, basically we should ensure that they should be equally made. It's not like, if we have like, let's say 2 partitions, and we have 1,000 records. Okay, let's say 100. And if we define the data such that on one partition or one node there are like 900 records, and the other node it's only 100 records, that doesn't ensure performance, right? Because one node is having 900 records, which is like huge amount of data, and the other node is 100, so that doesn't increase the performance or causes problems. So we need to make sure that these partitions by which we are defining should be as equal size as possible. And it all depends on your project, your design of the job, because sometimes when we use aggregator stage it may not be possible. So yeah, it all depends on the design. But yeah, most of the time we need to make sure that it's as equal as possible. So yeah, as I said, it's ideal for handling huge volumes of data. So that's a partition parallelism. I have, to make it more clear, I have given diagrams. So yeah, let's say the first one is source, and the next is like any stage, simple design, and the last one is target. So what's happening is the source stage, we do have only one source stage, but my config file has like 4 nodes. Okay, because my config file in this particular job is four nodes, 4 nodal config. So my every stage is being splitted into 4, every stage. So let's have, okay, I have taken like 10 million records. So I have 10 million records from a source. So once I have loaded 10 million records in my source, this source is being split into 4. So 4 is like 2.5 million records each. So each one is has 2.5, each source stage has 2.5 million records. And each, let's say this is transformer stage. So this the first partition is dealing with the first, and then writing to the target 2.5, and then 2.5 again, then 2.5 again, then 2.5 again. It's like node by node, node by node. Once it reaches here, everything is collected back and written to the single node. So that's how it works. So basically 2.5, 2.5, 2.5, 2.5, right? So 4 2.5s makes like ensuring load balance, and obviously when we have like enough balance, it leads to better performance. It's like it's like I don't know how many people played seesaw. It's like up and down, up and down. One person sit on the other side and one person. If it's like almost equal persons, then it's more fun, right? One goes down and one goes up. But if it's like more like a bigger guy is sat on one side, and the very thin or small guy is sat on one other side, it's no more fun, it's waste of time, right? So yeah, exactly, that's how it works. So yeah, we just need to make sure load balancing and for better performance. So but the common practice is we combine this pipeline and partition parallelism. It's not like we choose this partition and this thing. It's like we just combine this, because the stages like the process partition data, right? Because I said in my previous slide, the partitions, the stages are partition the data. And pipeline, how it comes into action is, as soon as this 2.5 million records from the source stage is written, it doesn't wait for the other 2.5 to be written. So yeah, that's how. And even in one partition, it doesn't wait for like all the 2.5 records to be written and then pass on to the next stage. It may happen that like 10,000 records are written, and as soon as the 10,000 records are written, it's passed on to the next stage. It doesn't wait for all the 2.5 on each node. So it's obviously pipeline, right? So yeah, that's how it's working. So we have the data is partitioned and it's processing simultaneously. So obviously we do have higher and higher performance. So yeah, so this is the best practice to do. And now we come to the partitioning techniques. Now coming to the different partitioning techniques. So this is the most important thing which we need to deal before designing our jobs, because yeah, this partitioning techniques, the way we choose the partitioning techniques basically defines the job, and yeah, ensures everything is like perfect. So yeah, we need to, this is really important. So yeah, so basically partitioning, we know that obviously parallel jobs are divided into multiple partitions and it's processing and everything, right? So we really you might be saying to yourself, it's enough that it's making partitions and it's running faster, right? So what is the use of these techniques? But there will be like certain circumstances where you need to take responsibility for this partitioning. So that's how like once you have identified where you want to partition data and which method works for which stage, which is the best method to use for that particular stage. So yeah, that's basically the most important thing which you need to be considered while designing your parallel job. Because if the wrong or the other partitioning technique is used instead of the right one, it's gonna mess up your job, and that leads to performance issues and all other things. So yeah, better be careful. So yeah, basically there are I say like a lot of different types, but the mostly frequently used are like round robin, hash, same. These are like more frequently used. And other one, I mean, we do have like probably nine, I guess. Yep, eight and nine. So yeah, the other which we use rarely are, I mean, limited use. We do use them, but it depends on the stage. Like entire, it's only, I mean, it's mostly used when it's lookup. When we have like lookup stage, that's when we need to use entire partitioning. And all the others like random, range, modulus, DB2, we need not worry about that because those are very 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 rarely used, trust me. And the other one is auto, which is like default one. I explain each of them with pretty nice diagrams, so yeah, bear with me for just like 20 more minutes. Okay, so coming to the round robin partitioner, let's deal with first round robin. So round robin, let's say like we do have a table with 6 records. Let's say 1 2 3 4 5 6. We have like serial number and then name. Okay, so what happens, and let's say my job I'm designing, let's I define my config file to use only 2 nodes. Okay, so yeah, we do have only 2 nodes. So let's see how what's happening if I choose round robin technique. So what happens is when I have round robin, right? So round robin is when I have 2 nodes, the first record is written to the first node, and then second record is written to the second node. Then third record, round robin, like first to first, second to second, and third to first, and then that way, like round robin. It always rotates between 2 nodes. If you have 4 nodes, so one first, I mean, first record is written to first node, second record is written to second node, third to third node, fourth to fourth node, and then the fifth node, I mean fifth record is again written to the first node. So that's how it works, round robin partitioning technique. So basically, it's always, I mean, approximately it creates like even sized or equal sized partitions. This is basically used, I mean normally used when data stage initially partitions the data. So yeah, so that's round robin partitioner. And now coming to the random partitioner. Random, as the name says, it 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 need not worry about anything. So it just does I mean it just does as it likes. No particular rule or nothing. So just random partitioning. It, I mean, the records are just randomly distributed across all the nodes defined as per your config file in that job. So yeah, I mean random partitioning also basically balances the partitions of input data set, so that, I mean, each processing node receives an approximately, I mean, it makes sure that each processing node receives approximately the same amount of data. It may have sometimes like slightly higher overhead, I mean, rather than round robin, because of the extra processing. Because for every column, every I mean for every record to be written, a random value is generated for each record. So because it first need to generate a random value and then return to the nodes based on that random value, it might take little process. So yeah, it's little overhead over round robin. So yep, that's random for you guys. And then next come to range. Okay, so range partitioning, it's like basically let's say range, right? We give some range, so it partitions as per that range. So that's how it works. So with my example, let's say I have like 6 records, right? So let's say I have given I have like, because it's my 2 node, my config file, I mean my nodal is sorry, my nodes are just 2, so I'm defining a range for it. I'm just saying it like when you see records from 1 to 3, write them to first node, and when do you see the records 4 to 6, then write to the second node. So yeah, that's how it works. So basically the range partitioning technique, basically it says like guarantees that all records with the same partitioning key values are assigned to the same partition. So I mean the same partitioning values are assigned to the same partition. So that's and yeah, it almost creates equal size of nodes to perform, I mean to balance the work on each node. So yep, so that's range partitioning. Basically we define a specific range for that partition, and then use that. You need not worry, it's not really used. It's I mean I didn't have an apt example here, but it's probably used like when you have like huge volume of data with people age from like 5, let's say insurance, like 5 to 80 years. Then and someone says, okay, so I need those candidates who have like let's say I need to make categories of like 5 to 10 people, and 10 to 40, and 40 to 80 or something. So that's how you can use range. So you define that key as age, you define the key field as age, and based on that key field you can just choose your range, and that's how it works. And the same partitioning as the name suggests, it really doesn't do anything. It just it's not really worried about the partitioning. The thing what happens here is it just performs like no repartitioning or anything. Just takes the input data, I mean just take the input, the partitions output. I mean let's say we have like what is this, 1 3 5, so 1 2, okay, so this is round robin partitioning, right? Because the first record is written to the first node, second record is written to the second node, and then the third again round robin. So yeah, so what it's basically doing is this the first round robin, it's not doing anything, just it's partitioning the same input data from the previous stage to the other next stage. So we are just making it same. We are just when we choose same partitioning technique, it means that I'm telling data stage not to do anything, just move the same partitionings from this stage, from the preceding stage to the next stage. So yeah, that's how it works. I'm sorry guys, I see that it's 3 is Pam or something. I'm sorry, I messed up. Okay, yeah, probably I messed up with the name. So yeah, need not worry about that. But anything, what's important is basically records stay on the same processing node, and they are not a repartition, just passing from the preceding stage to the next stage. So that's how it works. And next, coming to the entire partitioning. Entire partitioning is important. We use it in what's that, lookup stage. Sorry, yeah, so we use it in lookup stage. When we use lookup stage, we need to use this entire partitioning tech for obvious reasons. Because okay, let's an example. So I have taken these 3 records. Okay, so if you remember, okay, let's make an example here. If you remember from my server stage, I told about hash file stage, right? So hash file, instead of hash file we have lookup stage. I told you in that video that instead of hash file stage in parallel, we do have lookup stage. I mean instead of hash file we do have lookup stage. It's just replacing lookup. So yeah, it's same as that. So yeah, when you if you didn't follow my this thing, just please refer back to my probably 4th video, I guess 4th, or yeah, probably should be 4th. Yeah, 4th video on hashed file stage. So yeah, that will make it very clear why we need to choose entire partitioning. So basically I mean entire partitioning is like every processing node receives the complete dataset as input. See, I have 3 records, and each node is like taken for 3 records. Because why is that? Because why is that explains, I mean let me explain. Okay, so you're having lookup, right? So you have the input data, and you're having basically lookup on this input data. So to have the lookup on this input data, all the records need to be there in the lookup stage, right? Because if you don't have, like, let's say we have 5 records here and we don't have enough records, it doesn't make sense to reference or look up these records. So yeah, that's the reason we need to have like all the three, whatever records we have on this, we need to have like entire, so it's writing to each node. So when all the records are written to the next stage, that stage basically is looking up, the that stage is basically trying to look up with the other stage. So that's how it works. I'm not sure if it's made clear, but yeah, I'm really sure if you see my hashed while video, yeah, it would make pretty clear. So yeah, let's let me just retell it. Basically, to have reference data to be looked up, each node is to be written with the same as the input data, so that, like, basically it's need to access the end, because we need to have like the reference thing. It Each node need to have access for the entire input data, so that it could have like proper referencing, and we could have like proper output. So yeah, that's it. And next, coming to the modulus partitioning. Modulus partitioning, I think you should know about that, because it's nothing. We don't use it. I can say we don't use it. To be honest, I didn't use it till now, so yeah, I did not worry about that. So let me explain just theoretical part. So modulus partitioning is like, what do I say? Modulus part, like, basically we have like a key column, and that key column is based on that key column and the number of partitions we have, we do modulus function. So the function, the formula is partition number, which is like, which we need to define, which partition number for each record is calculated. Basically, when we have like different columns, so for each record, a partition number is created. So the formula for that the calculation for that partition number is like field name mod number of partitions. So basically, this field name is a numeric field of the input data set, and the number of partitions is like number of the processing nodes. Because I have been dealing with only two nodal configuration in this example, let's say two. So yeah, field name modulus 2. So uh, you have a certain value, right? You have like modulus like 0, 1, 2, or 3. So when you have like input data, numeric field, and then modulus number of partitions, so it's going to end up with some value like 1, 2, or 3. So depending on that, you will have your partitioning on which node to be written and all that. You need not worry about that. That's not the one which we use. So yeah, that's pretty much about modulus stage. And now coming to the DB2, this is also not really an important stage. It's, yeah, but let me just explain you. So DB2 is like basically partitions the data. DB2 is like a database, like Oracle. It's basically database. So yeah, it's DB2 partition in the sense it partitions the same way that DB2 would partition. It doesn't. It makes sense, but yeah. Okay, let's let's not get into that. For example, let's say like you need to, if you use this method to partition an input dataset containing like update information for an existing DB2 table, then records are assigned to the processing node containing the corresponding DB2 record. I hope you got it. Okay, if not, just leave it. Don't worry about it too much. And basically what happens during DB2 stage is, during the execution of this parallel operator, both the input record and the DB2 table record are written together to the local processing node. So any reads, so yeah, that's how DB2 partitioning happens. And the auto partitioning is the other thing. Auto means it's a default option. When you choose auto, you need not you're basically saying that data stage, I don't know or I don't want to choose any partitioning technique, so just choose whatever you want. So that's how we are telling that's what we are telling to the data stage. So auto, it's basically, it chooses the best partitioning method depending on the like mode of execution of the current stage and the preceding stage. So the number of nodes and available and all that stuff. But it's not an not at all an not at all a good option to choose auto in the real time, because it sometimes I don't know, for some reasons it doesn't choose the right partitioning technique. Or sometimes, I mean, when you have like huge volumes of data, obviously in like real time we do have like 100 million records coming each day. So for some reason I think it doesn't work out well. So yeah, you can learn about that, but don't use it often, because yeah, choose a right partitioning technique for right stages. So, and now coming to the hash partitioning, which is like the most important partitioning technique. So what's happening with this hash partitioning technique is, basically we define a key value. Key value or key column. Like, let's say we have 4 columns and we need to choose at least one primary key column, which is called hash key. So we can define more than one column. It's up to you. It depends on how narrow you can bring the data, so that it could be, your results could be more specified. Yeah, but at least one key column should be specified. And what happens when you choose, so once you define the key column, what happens is, based on that key column, records with that same key field will be assigned to the same processing node. Let's say example, we have like duplicates and all that stuff. I'll make it clear. So we have like one. Okay, let me move to the another thing. Okay, let's take this entire thing example. Okay, so let's say I have like one first record 3 times, repeating 3 times, second record repeating 3 times, third and 3 times. So every record, each record is repeating 3 times. Okay, so I want to count how many I want to just count. Or yeah, let's say it doesn't make sense, but just an example. So let's say I want to count the serial numbers. So we have like one, right? So I said we have three same record. So 1 2 3, so the sum of my serial number is 3. For Pam, the second record, it's 3 times repeated again, so it should be 6. And for third record it should be 9, right? So how do I do that? If I just define this any other partitioning technique, it doesn't make sense, because each time when I choose this node partitions, it choose like one over here, or and the first one over here, the second one, I mean round robin, first one over here, second one over here, and third one over here. So when we have 2 1s over here and 1 1 over here, it doesn't make sense to add up, right? So yeah, that's when we go for hash partitioning. That's more important. So when we define hash partitioning, we are telling data stage that whenever you see serial number as 1, just put all those 1 into one partition. And whenever you see 2, let's put all those 2's into other column. And 3, and then 3, I mean group it, just group by the key partitioning value. So that once you have group, you can just like move to the next stage, like say, let's say aggregator stage. So you can say like calculate on this column, so that my output would be 3 for Jim, and 6 for Pam, and Mike as 9. So that's how it works. So yeah, that's the most important thing about the hash stage. So you might be wondering, how do I know when to use hash stage and all that, right? So the most I remember I remember that way. Whenever you see a certain specific stage having an option, having a mandatory option to choose a key field or key column, that's when you use hash partitioning technique. So because it doesn't ensure an even distribution between the partitions, right? Because you might be having 3 ones or 2 Pams or 4 mics, so it doesn't have like even partitions. So yeah, that's a problem. And the indicator fields are poor choices for hash case. Indicator fields in the sense, like male or female, like gender, let's say gender, male or female, M or F, right? Or yes or no questions, yes or no columns. So those doesn't make sense for choosing hash keys, because when you choose that, you have lots of data, you have only two columns, yes or no. So when you group by yes or no, you're not actually narrowing your data, you're just making it like 100% is data is filtered into 50%, but it doesn't make any sense. So based on the key column, based on the key column, you can define any number of key columns with mandatory as one. And I mean, the key columns should not be more than obviously the number of columns we present in your data, right? So yeah, that's how it works. So I mean, the best example I could give is like, let's say we have a zip code field. You're analyzing for a state. Okay, so when you analyze a zip code field for a state, for by like first few so if you choose like one or two digits of a zip code, it doesn't make sense, because in the same state, the zip code, it has like the first two or three digits might be same, right? So yeah, so when you have like three or four digits, when you choose like the primary key and all that stuff transformations, yeah, I think it's not a right example. It's making it more confusion. But yeah, I mean, you can just narrow your things so that it would be more appropriate for hashtags to understand that, okay, so based on the key column, it's grouping. So I need to calculate, or I need to work on this grouping things. So that's how it works. So that's hash partitioning. And the other thing is preserve partitioning. Preserve partitioning, it's an option in most of the stages when you define your partitioning technique. It gives an option for preserve partitioning. It means that it's basically asking us whether the data, or whether the partitioning technique in the previous stages, we need to preserve it or clear it, or just move it to the next stage. So yeah, that's what it's asking. So I mean, let's say we have like three stages. Okay, source and any transformer stage, or any target stage. So what's happening is, always preserve partitioning flag, it's always in default stage, it's the best option to do. So but the other options is, when we have like preserve party when we okay so when we basically, it has three options: set, clear, and propagate. So when you choose clear, you are saying that the partitioning which was done in the previous stage, I don't really care about the partitioning which was done in the previous stage. Let me clear that partitioning in this stage, and I'll define my own partitioning, or I'll choose a new partitioning technique in this stage, and then moving it to the next stage. So you're basically clearing the first partitioning technique. So that's what it's clear. And if it's set, it means that if it's set, it means that on I mean you're basically set to propagate, like okay, so if you propagate, it means that I'm good with the partitioning technique which I have chosen in my previous stages. So just move on, just propagate the same partitioning technique to the next stage. So yeah, so that's how it works. And the other thing is, I mean, some stages we can just have like a set option too. In this, like basically it has like basically we are just saying like this basically we are just flagging this I mean, yeah, we're basically telling the output link that the setting from the stage that like the previous stage in the job has set, so you need not worry about anything. So yeah, that's how it works. So that's preserve partitioning technique. Basically they call preserve partitioning flag. So yeah, so you need not worry about this. Just a brief idea about what's this, because when we choose our partitioning technique, it's the other one which we need to worry about. So just this clears. So you need not worry about set. It's just clear and propagate are more important than set. Okay, and the other thing which I want to tell before we move on to the designing is, it's a most important thing, which is runtime column propagation. They call it RCP. There are many questions regarding this RCP. So you might be thinking runtime column propagation, so you can just frame it yourself, but let me explain now. So basically data stage, like we can when the data is not defined, when like metadata in the sense the columns, in the columns tab, in the stages. So when the columns or the metadata is not defined, or like partially defined, so partially defined, but we do have like a few extra columns, we do okay. So let's say we have only let's say we have like 10 columns, 10 columns, but we defined only 5 columns. So what about the other 5 columns? We didn't define them, right? But when I enable this runtime column propagation, what does this do is, even though I define 5 columns, the other 5 columns which I didn't define, they are treated as extra columns, and once they uncounted by the data stage, they are just propagated to the next stage, and to the next stage, and to the next stage, till the target. I mean, it basically the propagates to the rest of the job, to the complete job. So yeah, that's how it works. I mean to say, basically it the data stage will adopt these extra columns encountered and then propagate them through all the job. So this is known as runtime column propagation, and this runtime column propagation can be enabled through administrator client. Administrator client, I'll show you. I'll show you in this thing. I'll show how to enable the runtime column propagation. When you click on the administrator client, you can just have like a runtime column propagation. So you need to click that. I mean, check that box. Uh, yeah, and the other thing is, when you use schema file, this runtime column propagation should be enabled. I'll tell what is a schema file in probably like next video. So yeah, you should always ensure that the runtime RCP or runtime column propagation is turned on if you want to use a schema file to define your metadata. And yeah, you might be thinking that because it's pretty cool option, right? We need not define whole data. But what happens if you always check that? What happens is, let's say in real time we don't deal with 1,000 or 2,000 records, we deal with millions of records. So you need to always choose only those records which you really need to write to the target, or which you really need to transform or perform any functions. And let's say we have like 10 records, and you are calculating or you're worrying about only 4 records. So 4 records, you're dealing with only 4 records, so it doesn't make sense for if you enable runtime column propagation. It doesn't make sense. Let's say, okay, let's make a clear example. You have 10 records, okay? So you have 10 records, and the business, which is the client, the requirement says that you need to only work for the 4 columns in the four columns in those 10 columns, okay? So you're not really worrying about the other 6 columns. I'm sorry, yeah, other 6 columns. So if your business, if your client is saying that you need not write to the target stage those 6 columns, why to waste resources passing on to each stage and then filtering it out? Just filter it out in the initial stage, source stage. So yeah, that's how you need that's when you need not enable runtime column propagation, because if you enable runtime column propagation for every job, it makes a mess. When you have like 10 million records, and you're writing only 1 million records, the other 9 million records, even though you're not using them, they are propagating. So that's complete waste of resources. So yeah, it you need to be more specific when you need to choose runtime column propagation, because if it's an important interview question. So they asked us like, if RCP, could you enable RCP for any job? No, we could not enable. We can enable, but it's not a good option to enable RCP for every job, because that leads to performance issues in the real time. So yep, that's how it works. So that's all, guys. That's all in this video. I just want to give a brief introduction about the things which we will be dealing in designing the parallel jobs, I should say. So yeah, in my next stage, in my I mean sorry, in my I'm more involved in data stage, so every time I'm saying it's stage. Yeah, in my next video, I'd be designing. I mean, I'll be dealing with each stage. So I thought I would not make longer videos. So I thought of coming with shorter I mean, shorter in the sense like only one stage in one video. So yeah, so I'll come up with probably a dataset stage, or yeah, I mean, I didn't really come. I mean, I didn't really picture myself, so I'm not